Hello, welcome back to ELC 101. We're covering process diagrams, which is in Chapter 12. So these are the diagrams that are most likely to be used by and seen and used by a process operator, a process technician, or an instrument technician. The block flow diagram, also known as a BFD, process flow diagram, also known as a PFD, and a piping and instrumentation diagram, also known as a P&ID. You probably heard of these many times. CPO people that are taking that program have heard of each of these diagrams many times, and there are several others, and we'll talk about them. And they do go in order from the least and the most simplified to the least difficult to the more difficult and the more complex. The block flow diagram shows the flow scheme very simple, sequentially block form. So you start out with your feed, go to your feed storage and metering, you go to a reaction, and again, you don't know what's going on exactly here. You don't know how it's reacting. You don't know what kind of reactor, but this is the main block reactor, cooling, separation to your storage. Here you use a refrigeration for some part of that separation, and then it shows a recycle line. Coming back here, it's just showing you where one product is going and then where the other two products are coming out of the process. And again, red, usually left to right. The process flow diagram is less detailed than a P&ID, and it tells you to understand how the actual process works. But what I mean by that, it provides your material and your energy and heat balances in your chemical process. It gives you the major pieces of equipment, and it gives you all the different flows all along the different ways and the operating conditions. Okay, so in this particular instance, these are used to help size all the different pieces of equipment. They're used to size your piping, your all the different pipes here, your valves, and the different exchangers, heat exchangers. Okay, so and your pumps. So that's important to know. That's one of the big pluses of having a PFD, and it's very important for you as a process operator, technician, instrument technician to have this available to you. The next more difficult one is the P&ID diagram. This shows all the piping and vessels in the process flow, gives you the instrumentation, and all the control strategy is laid out here for you. It gives you all the different types of piping as well, whether instrument air and signals coming here, electrical or not, and gives you basic mechanical design and details. All right. So here's an example of what this would look like in the field of reactor, right? This is a control valve, piping inside the reactor, cooling, temperature recorder, and then over here a transmitter. This is what it looks like on the diagram. These diagrams are always coming in a drawing package, especially when you're doing a plant or a new processes design or any revisions and updates. When you're in a complete drawing package, also you'll get a site plan, utility drawings, and loop diagrams. The loop diagrams will list all of the different loops and the control strategies per equipment piece in a really nice layout for you to look at. Okay. Then you have legends and symbols. PFDs, process flow diagrams, and P&IDs should have an associated legend with that, and it just tells you what each of the symbols mean. Each drawing type reveals a specific but usually different piece of information about the actual process, so it's good to know. P&IDs also will not only show the instrument and the loops, but any instrument that will be in the field, and that's what each of these mean, and we're going to go into detail about that. All of these drawings collectively help you understand and troubleshoot all the different problems that you can have with the process flow in the whole unit and the process. Okay, so how do we get these drawings to look the way they do and all of us understand what they mean? Well, that's what a standard's all about. A standard is something, considered by an authority, or it's a general consent as a basis or a comparison. And then it's an average or normal requirement, quality, quantity, level, or grade. ISA is the big name. They're called the Instrumentation Systems and Automation Society, and it's just one of many. I'm sure you've heard of ASME and ANSI. ASME is the American Standards for Mechanical Engineer, and ANSI is the American National Standards Institute. So I'm sure you've heard about them and a few others as well. And there's also ISA, and I thought it was Instrument Society of America. So that might be another another organization. So there are very many of them. Unfortunately, there's a lot of acronyms that mean the same thing. But what is the objective of a standard? Well, it provides a road to make sure that it's common, right, between the processes, companies, industries, and even other countries, right? Everyone looking at a picture will know what it means, right? That's what pictures are all really good about. And the standards, too, help make you design your process to be safer and also reducing costs. So, and if you do the same thing the same way all the time and you all use a standard piece of equipment, it'll help with the parts and replacements. Okay, you don't generally draw a P&ID like this, right? Because this is not very practical, and it isn't very CAD friendly. So we don't draw them like that, but we build it using the different symbols in the circles to represent things. So we'll go into that. We'll give you tag numbers. They're letters and numbers, and they're within the instrument to identify the type and the function of the device. So let's do that. We've done this before, and you pretty much know this, but I want to review it. P, L, F, and T are your first numbers. That's your process variable that you're measuring. Pressure, level, flow, or temperature. And sometimes you'll have composition. That can be an A, or P, like pH might be an analytical piece of information. The A stands for analytical. Then the succeeding letters will give you the designated function and of the component or modify the meaning of the first letter. So we have I. Sometimes you'll see LIC, a level indicating controller. You might see R for recorder, and you might see T for transmitter. Have you seen TT, temperature transmitter, like 101? And then the loop number at the bottom goes with all of them. And as we've done it, we just did it in the last one. The last couple of chapters we talked about the naming every part of the loop, and they all have some part of these letters, and then they all have the same number because they're all connected to the same loop. So let's look at this one. So you start with a temperature indicating 206. That's your temperature indicator. Same loop number. TT is the transmitter connected with that indicator. The indicator feeds it to a transmitter. The transmitter goes to the recording controller. So they all have the same loop number, and then they're just telling you what their functions are. This is in the field, this is in the field, and this is in the field, and we're going to learn how to read that. Sometimes you see TE, a temperature element. Again, we've seen them before in the past, and we're going to talk about what each of these are. And your tables and their figures are in pages 249 to 257. Look through them in your textbook. They're really good to look at. All right, let's look at these now. When you're looking at your P&ID, generally you'll see these three ways to see them. Number one, with no line. That means that your instrument is mounted in the field. That's when a field operator will go, is in the process, right? So if you have a temperature element, it has to be inside the liquid or the gaseous state, whatever it is you're measuring the temperature of. So you know that's in the field, no line. This line indicates it's mounted in the control room or it's fed to the DCS, so you have that line. The control room operator sees that. This dotted line means it's out of sight and you're not able to see it. So the DCS, the distributed control system, will have these, okay, and you'll see them in the control room. This will be in the plant, and this will be not accessible. So here's again another summary of that. It's in your page 249 to 257. Please look over them. They're really good. It'll help you understand that. Okay, now I want to go over piping and connection also in your book. This piping is generally this much thick straight line, or however it just goes from, it shows you the piping of it. The process connections are the thin lines. However, electrical signals are these dashed lines. You'll see them all over, and we'll see them when we get to the next couple of examples. A pneumatic signal, and we've talked about this before, is a straight line with these hashtags. Okay, it's important to know. That's always giving you an error, instrument error signal. These little circles are data links that come from wherever, it might be a computer. And then a capillary tubing for a linked system, for a field system, is this symbol here. Excuse me, this indicates a hydraulic system, okay? So this little L, just know for that. And then this is to do with a electromagnetic or sonic signal. The valves. Now, you have seen many of these, and you'll always see them. These are always indicative of a control valve when you're looking at a P&ID, and these are always indicative of a solenoid. That's usually the on-off valve. So you'll see all these different ones, and you will just over and over again, you'll see different symbols for different, what they mean. Just make sure you know your legend and look at them, and ask when you go to work, what is the actual society of symbols that they use, and where you can get a legend to learn it, and just make sure you understand it. So that's important. That's on you. Now, the ISA produces the most prominent instrumentation drawing standard called ISA S5.1. Okay, this is important. It comprises both specific symbols and denoting functionality and a coded system which gives you more functionality. And again, if you look in equipment, your text, you'll see equipment symbols, line symbols, and your valves. Both of these we just talked about. And you'll see some more equipment symbols in your text. It's very important for you to review them. All right, let's look at a typical P&ID. So this is a heat exchanger. Okay, this is a symbol, the generic symbol, if you look at it, for equipment of a heat exchanger. It doesn't tell us if it's a shell on tube heat exchanger. It doesn't tell us if it's a plate and frame heat exchanger. Okay, it's just the symbol. On this side, you'll see cold feedstock goes in and then the hot feedstock comes out. Up here, you see steam coming in, and on the out, you'll see the condensate. Over here, you see all the different instrumentation that's for the steam side. There's a flow transmitter in the line and a valve. There's a temperature transmitter, there's a hand valve, and there's a control valve. And on this side, there's nothing. Over here, you have a pump, and over here, you have a flow transmitter, you have a flow control valve, and on this side, you just have a temperature on this end, okay? Now, this is what's important for you to understand, what these lines mean. The dashed lines, all of these dashed lines, mean it's an electrical signal, a 4 to 20 milliamp. Here it is again, here, here, and here, and over here. The hashed lines are the pneumatics. So let's trace one of these, all right? So we have flow. We come from the pump, pumps in the cold feedstock through a flow transmitter. The flow transmitter is located in the field, no line. It sends an electrical signal to the controller, flow indicating controller. They're all labeled 101. That's in the DCS control room. That's what the line means. The DCS sends out an output that is also electrical and usually milliamps to a transducer, an I to P transducer. So FY101, that takes the current I to P pneumatic and then sends that signal to your flow control valve 101. And there's your final loop, a whole loop. Over here is another loop. So we'll go over that in the next slide. So again, the feedstock is pumped. And we just talked about this, right? Through the flow. Now let's talk about the temperature control. There's a temperature transmitter 102 in this line, and that's not even an element, it's just a transmitter. Takes it and it sends it to the temperature indicating and recording controller 102. Again, all 102. Over here it's showing TAH 100 and TAL 100. This tells me that there's a high alarm and there's a low alarm. That's what these are. These are electronically signaled based on the current coming from this transmitter, and then it'll signal a high or a low and do whatever an alarm tells it to do or just warns the operator. Then another electric signal comes out to the converter again, the transducer T to Y, 102. The I to P sends out a pneumatic signal to the control valve, TC, temperature control valve 102. And there's your whole loop. It's important to know. Over here, we have different signals again, right? So let's look at this one. FT103 supplies a signal to the recorder. FR103, which is now where? In the control room. This is in the field. Electronic signal. It's just reading the flow. What type of flow devices? Well, we're not sure, but these look like orifice type. They could be DP cells too, so we don't know. So let's talk about the next one. The remote mounted hand switch turns the pump on and off. Here's your pump. There's a switch in the field and then on or off. Okay, and this is in the control room and it sends a signal. And then again, the loop. Over here you have, again, these are the alarms. These are in the control room and they're electronically signaled. So remember, the line tells you where it is located. Okay, here's the final one. We're looking at an open tank and a level gauge and a level indicating transmitter 101. They're all 101. It's feeding information to the controller, again, electronically. Electrical to the FIC. It's also electrical, flow indicating controller. And then the transmitter comes over here and is fed to that. The set point sets that flow to tell the controller what to do. Another electrical, I to P. Over here, current to pneumatic, pneumatic to your control valve. So straightforward flow. Again, this is a cascaded loop. So you might want to just study this a little. If you don't understand, let me know and I can go over it with you, no problem. So I'm not sure about doing a test yet, but I'm thinking this might just be a really good way to do a simple open book test for you to understand the loops. But you're going to be doing that in your project, which we'll be covering next. So I'll see you soon. Okay, I'll be talking to you in a few more minutes. Have a great night.